Okay, today we're going to look at constructing truth tables. So if you recall, the negation of a statement will always have the opposite truth value of the original statement. If a statement P is false, then its negation is true, and if a statement P is true, its negation is false. To create a truth table for the negation of a statement P, add a column with a heading P, a heading of not P, and for each row, input a truth value with the opposite value of the value listed in the column for P, as you see below. So we start out with P here. And what are the two possibilities for P? True and false. Then we go to not P. And if P is true, not P is false. And if P is false, not P is true. Conjunctions and disjunctions are compound statements formed when two logical statements combine with the connectives and or. How does that change the number of possible outcomes and thus determine the number of rows in our truth table? Multiplication principle, also known as fundamental counting principle, states that the number of ways you can select an item from a group of n items and another item from a group of m items is the equal the product of n times m. Because each proposition P and Q has two possible outcomes, true or false, the multiplication principle states that there will be possible outcomes true, 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 false, false, true, and false, false. Below is a truth table of four possible outcomes for two propositions P and Q. And the way to do this is systematically. We have P is Q, true is true, P is true, Q is false, P is false, Q is true, and P is false, Q is false. A conjunction is a logical statement. For a conjunction to be true, both the statements that make up the conjunction must be true. If at least one of the statements is false, the and statement is false. A disjunction is a logical inclusive or statement, which means that a disjunction is true if one or both statements that make it are true. The only way a logical inclusive or statement is false is if both statements that make up the disjunction are false. Excuse me. So, an and statement, only true with true, true. Or statement, only false with false, false. And here again, we continued our truth table, looking at and. We look at all the possibilities, and the only time and is true is when both statements are true. All the rest are false. Now with a disjunction or statement, if one of them is true or both of them is true, it's true. So the only time it's false when it's false, false. Okay, so construct a truth table to analyze all the possible outcomes for each of the following arguments. And the first one is P and not Q. I went a little overboard with my notes here, so let's go to this. I'm looking at P, oops, P and not Q. So I have two statements. I need to look at those. I need P and Q. Then I need not Q, and then I can go to P and not Q. So how does this work? Well, start with P. P can be true, true, false, false. So when P is true, Q can be true or false. And when it's false, Q can be true or false. So now not Q. If Q is true, not Q is false. If Q is false, not Q is true. And then false again and true again. Now we have an and statement. So both have to be true for it to be true. And we're looking at P and not Q. Well, I can see here, Q, not Q is false, so this is false. Here, they're both true, so it's true there. Here, they're both false, so it's false. And here, P is false, so it's false. The next one we look at is a little bit different. It's not P or Q. So again, we have our P and our Q. Then we're going to have a P or Q. Then I'm going to have not P or Q. Oops, Q. Q. There we go. So again, P, true, true, false, false, true, false, true, false. P or Q. So when one of them is true or both of them are true, it's true. Well, P is true here and here, so it's going to be true. Q is true here, so this is true, and we have a false. Then we're saying not P or Q. So we take the negation of that previous of here. We get false, 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 true. And the last one here is P and not Q or R. So now we have three. So we're looking at 2 times 2 times 2, 8, which is what we have here. So we start out with P, and it's going to be a little different. Then we're going to need Q. And we're going to need R. What else do we need? Not Q. Right there. And then we need P and not Q. And not Q. And then we need P and not Q or R. So let's look at how this works with 3. Well, we start off, half of them are going to be true for P. Start off with the first half. False, false, false. Now we can have true, false, or true. Let's go true, true. True, true. True, false, false, true, false, false. No, we don't have enough lines here. Then we have true, true again, true and false, and then false, false again, and true and false. So now we're looking at not Q. So we go down Q and we do the opposite. False, false, true, true, false, false, true, true. Now I'm looking at P and not Q. So I'm looking at P here and not Q. Well, Q is false, so it's going to be not Q is false, and it's going to be false here. I do have true, true, and true, true here. And then for the rest of these, P is false, so they're going to be false. Now, here we have P and not Q. So anytime P and not Q is true, P and not Q or R is going to be true. So I have these two here I know are true because this one's true. Then I look here and I see that R is true here, here, which I already have, here, and here. And then the rest will be false. And that is how the truth tables are done. You have to construct to what you're aiming for. So now we talk about validity. The validity of a truth table or a compound statement. A logical statement is valid if it is always true, regardless of the truth values of its components. To test the validity of a compound statement, construct a truth table to analyze all possible outcomes. If the last column representing the complete statement contains only true values, the statement is valid. So what do I have here? I think I put this all together. So we have two statements, P and Q. So standard true, true, false, false, true, false, true, false. Anytime you have two statements, that's what you're going to start with. Then for a not P, I have false, false, true, true. And for not Q, false, true, false, true. Now I'm looking at number one here, which is P or not Q. So here and here. And it's an or statement. So anytime one of them is true, it's true. So P is true in this first line and the second line, so we're good. And not P is true here and here. So this tells us that this is valid because it's true for every possible outcome. Now let's look at not P or not Q. So now we're looking here and here. And it's an or statement, so one of them has to be true for it to be true. Well, both are false there. One is true there, one is true there, and both are true there. However, I have this one false here, so it is not valid. And that finishes section 2.3, constructing truth tables.